calcium fire. All right.
I know it hasn't been long since our last one, but it's time for another molten salt electrolysis project. I've said before that this series of videos, where we focus on the electrolysis of molten salts in order to generate reactive metals and exotic elements, is going to be serialized in such a manner that we start off with the easy reactions to perform. So we started out with aluminium and sodium generation by the electrolysis of molten aluminium oxide and sodium hydroxide, both of which weren't too difficult with the right setup. We then moved on to generating lithium metal from lithium chloride. This was a little bit more challenging because of the generation of chlorine gas and the fact that the yield was heavily dependent on the type of electrode that we used as the cathode. We then tried making boron by the electrolysis of molten borax. That didn't work, so we're not going to count that. Today we're going to be stepping up the difficulty quite considerably once again, because today's project is going to involve attempts at making calcium metal. If you know a lot about calcium for some reason, you might know that the electrolytic generation of calcium metal is extremely difficult, both according to papers online and according to the history of the industry of making calcium metal. If we look all the way back to the first isolation of elemental calcium by Sir Humphry Davy, we'll find that he really struggled to generate elemental calcium from electrolysis of its molten salts, and instead had to rely on electrolysis of its aqueous salts in aqueous solution using a mercury cathode. The mercury, of course, amalgamates with the calcium, and then you can distill the mercury off later, leaving you with pure calcium metal. I believe Cody'sLab actually showed this really nicely in one of his recent videos on extracting calcium from bones, I think. As it turns out, even if you look at the complete history of industrial calcium production over the last couple of hundred years, you'll find extremely few examples of cases where it's been extracted from electrolysis of its molten salts. Basically, everyone who has tried this kind of reaction, generating calcium by molten electrolysis, says that it's extremely hard, and that includes scientific papers and also random people on the internet who have said that they've done it. The reason for this is the fact that calcium metal is actually generally very soluble in calcium salts. So molten calcium chloride, something like that, has a very significant solubility for calcium metal. And as a result, if you try generating calcium metal by the electrolysis of molten calcium chloride, the calcium metal will pretty much dissolve into the melt just as fast as you generate it. Nonetheless, we're going to have a go at it. So I got some calcium chloride from the hardware store. This is actually the smallest quantity of calcium chloride that I could get hold of. Calcium chloride, despite having the calcium solubility problem that I was just talking about, is generally the best option for this kind of electrolysis because it doesn't generate any weird products on the electrodes during the reaction. There are a couple of ways we can try to get around the calcium solubility problem in the calcium chloride melt. First option is to use an extremely high current density on the cathode. The cathode is, of course, where we generate the calcium by the reduction of calcium ions. We give electrons to calcium ions to form calcium metal. And if we keep the current density on the cathode high enough, we might be able to generate calcium faster than it dissolves back into the melt. It's unlikely because most references say that this needs to be done in an inert atmosphere in order to get it to work properly, but we are going to have a go. The second thing we can do, most references state that the only successful industrial electrolytic calcium production has been done using a cathode that you kind of raise out of the cell as you're generating the calcium. The idea behind this is that by removing the cathode slowly from the melt, the calcium that forms on the cathode surface is removed from contact with the calcium chloride, which stops it from dissolving, obviously. Once again, basically every reference I've found seems to say that we require an inert atmosphere to do this, so my hopes for this reaction are pretty low. If we do this simple molten electrolysis and it turns out to not work, which I'm finding to be highly likely because everyone has told me that it's basically impossible, I do have another reaction as a plan B. It's still a molten salt electrolysis procedure, still involving the electrolysis of calcium chloride. However, it won't generate calcium as a pure product. So I'm holding off on that one until we're absolutely certain that simple electrolysis of molten calcium chloride definitely won't work. For the actual reaction, in order to keep our current density on the cathode extremely high, what I'm going to use to melt down our calcium chloride as a crucible is a graphite crucible. We did this before for our aluminium project. What we're going to do is use the graphite crucible itself as the anode for the reaction. So the anode is going to be performing oxidation. It's going to oxidize chloride ions in the melt, take electrons away from them to form chlorine gas. For this reason, I will be wearing a mask during the reaction. And as I said, we're going to be using the crucible itself as the electrode to do that process. I'm thinking that the resulting really high surface area of the anode will allow a really high current, even with a small surface area of cathode submerged into the melt. And this will really help us to push a really high current density without pushing too many volts through the system. As a cathode, I'm just going to use a bit of steel wire, and as I said, I'm just going to slightly submerge it in the calcium chloride melt in order to maintain a really high current density. I think that's all I had to say about the reaction. Again, we'll get to the plan B reaction when we come to it, but for now, we're going to head out there and we're going to try to melt down some calcium chloride. I think the melting point is a little bit below 800 degrees Celsius, and then we're going to try electrolyzing it. So let's get to it. And that is everything set up. We have our electrodes ready. We have our calcium chloride in our crucible ready to go. So we're just going to wait for a sec for this to all melt, and then we'll start electrolysis. Looks like the calcium chloride we're trying to use isn't completely dry. That's to be expected. I suppose it is highly hygroscopic, but we're going to have to wait a little while for all of this water to come out of our calcium chloride before it can properly melt. Well, that took a lot of effort to melt, but we got there in the end. That looks like molten calcium chloride. So what we should be able to do is now electrolyze it. With just the very end of the iron wire dipped into the calcium chloride, if we now start up electrolysis, we should see some sort of reaction. Yes, we get something there. I've set that to 1 amp, and what we can already see is a whole bunch of bubbles coming off the cathode, which is probably indicative of some water still in the calcium chloride. That should stop in a few minutes. You can also see down there, though, I think, flames every now and again off the cathode with a clear orange flame. That's very representative of calcium. So hopefully in a sec we'll be able to increase that current to make a really high current density on the cathode, and then we'll see if we can actually make any calcium metal. Again, I doubt this is going to work when we turn the current up, but we might as well have a go. So we'll give it a few minutes to get rid of all the water from our melt, and then I'm going to put my mask on, and then we are going to set it to maybe 8 amps. Alrighty, that's 8 amps there. I've been trying on and off for the past, 15 minutes, 20 minutes, trying to get any kind of calcium product on our cathode. It's a very exciting electrolysis. There's lots of flames, lots of fire coming out the top, but we're not seeing any calcium metal at all. Everything that's burning up now seems to be actual tiny bits of calcium metal, but there's absolutely no way we could conceivably actually collect any of that calcium. It's not sticking to the cathode, it's burning up instantly with the chlorine that's being generated, and it's also, of course, dissolving into the melt. So without an inert atmosphere, which I don't have access to at this point, and certainly don't have the apparatus to handle it in this kind of temperature, we are not going to extract any calcium, I don't think. We're just seeing a whole lot of flames in there. Even with electrolysis stopped and the electrodes removed, you can still see
tiny little bits of flame in there. I don't know whether they come up on camera, but clearly there is calcium either dissolved in the melt, or there are bits of calcium floating around in there that are too small to collect. Alright, false alarm actually. Upon turning the cell off and taking the electrodes out, when the cell was being allowed to cool down, I found actually a small shiny globule of calcium metal floating in the molten calcium chloride melt. So I've set the cell back up. We're going to try this again. I'm going to leave this running at 8-9 amps for another 10-15 minutes. I'll turn the cell off again and see if the same thing happens and whether we can scoop out the calcium metal that we make. I did scoop out the calcium metal we made before, but then tragically I dropped it on the ground, and it was such a small bead of calcium and it looks just like a rock, so I'm not going to be able to find it in all of this concrete everywhere. So sadly, that piece of calcium is lost, but it was definitely metallic, so I'm hoping that if we try this again, we will actually be able to generate some more calcium, and I will be able to actually show it to you this time. And yes, after another 15 minutes of electrolysis, you can see we have actually made a small amount of calcium. It doesn't look like much at the moment. It doesn't look quite as shiny as it should because it has oxidized in the air a little bit. It's gone a little bit white. It's gone a little bit black. I'm also really struggling to take it off the scooper that I used to collect it because while the molten calcium chloride doesn't really stick to it, the actual calcium itself has really stuck. So I'm going to continue trying to get the calcium off this thing, and then we're going to continue electrolysis to see if we can make some more. There we are. I was able to remove a small amount of it from the scooper that I was using. This is about half of what we were able to extract in that first 15 minutes. I'm very sure this is calcium because it is, as you can see, rather shiny in places. So to actually test it properly, I'm going to chuck half of this, just this small one here. I'm going to chuck this in some water, and if it starts generating hydrogen, we know that we have actually made calcium here. All right, here's that calcium. If we chuck this in the water, oh yeah, excellent. That is definite hydrogen formation, and that is definite calcium. So that's excellent. Alrighty. That's the latest chunk of calcium there. We've got no reason to stop, really. I'm going to keep making more. While we've got the electrolysis running again, I just wanted to note one thing, and that is the fact that we really can't smell any chlorine coming off the cell. Every now and again I get a small whiff of it, but chlorine is really, the kind of gas where you know when you're dealing with a lot of it. And I can definitely say we're not dealing with much of it at all in this case. Certainly not the amount of chlorine that we would be expecting to obtain due to the electrolysis running at, I think that's running at 9.5 amps right now. So what I expect is happening is possibly our calcium chloride in the initial bottle that we got it from maybe had some calcium hydroxide or calcium oxide in there, which if they were added to the calcium chloride mixture would result in oxygen being generated on the anode instead of chlorine. And I think that's exactly what we're observing here.
Now that we've finished running the cell and everything is packed up, first of all, we'll get a look at our electrodes that we used. First of all is the cathode. So this is the iron steel wire that we were using to actually generate the calcium. We were using an extremely high current density on the very end here. Maybe about half a centimeter of this was pushing close to 10 amps of current the whole time for about an hour. So it's done pretty well. It is a cathode, so we're not actually expecting any corrosion to occur on the surface of the electrode here, but it is still quite impressive that we were able to push that much current through such a small area. I said before that most others who have tried similar processes to what we tried today haven't really yielded very good results, if any. So I think the super high current density that we actually were able to push through this electrode was what led us to successfully isolate calcium metal today. While we're on that note, I said at the very start of the video that I really wasn't expecting this simple electrolysis to work in making calcium metal, and we did have a plan B for making it. So seeing as it's completely unnecessary to try that method because we made calcium, I might as well tell you what it was. I bought online some metallic tin. You can see here what I was going to do as a second attempt was use this tin as a liquid tin cathode because calcium is more soluble in liquid tin than it is in liquid calcium chloride. So using tin as the cathode would allow calcium to alloy with the tin. It wouldn't be as good as making calcium directly as we did today, but we would have been able to make a calcium tin alloy, and I was going to show you what that looked like. But in the end, we made relatively pure calcium metal anyway, so there wasn't really any point to make the calcium tin alloy, I thought. Additionally, if we look at the anode, of course, this was our crucible that we were using for the extraction. It really has survived pretty well. You can't really see down in there because it's too dark, but maybe, no, not really. The graphite in the crucible itself has actually survived extremely well. We determined in our lithium video that graphite is really good at the chlorine generation anode reaction, and we're seeing the same thing here. We can use this many more times, I think, before this would start to dissolve away, so that's really good. And of course, the thing we really want to see is the calcium metal that we were actually able to make. So this is the calcium metal we were able to extract. All up, it's about 610 milligrams, which isn't the best yield, but I'm still pretty proud of it. Normally at the end of the video, I'd show you the properties of the metal that we made. So we did this with the sodium and the lithium. But from earlier in the video, you've already seen its reaction with water, and I don't really know what else to show you. If we get a closer look at them, you can see it's rather tarnished, but there are some shiny sections on the metal globules. And with that, I'm going to store all of these under a small amount of mineral oil to prevent them from further reacting with oxygen and nitrogen in the air. And that's that, calcium metal. I know I said it many times before, but I am very, very happy that we were able to actually make calcium metal, especially in its pure form. And honestly, it was one of the easier molten salt electrolysis processes I've done. Despite what it looked like with the flames and everything, it was a relatively well-behaved reaction, and we were capable of extracting a pretty consistent output over the 45 minutes to an hour that we were running the cell. And finally, with calcium successfully made, that brings our number of metals that we've successfully extracted by molten salt electrolysis up to 4. And I think that's the number where we can start calling it a collection. So we now have a collection of metals that we've made ourselves by electrolysis of molten salts, starting with, of course, aluminium, sodium, lithium, and calcium. I think that's pretty cool, and I'm very excited to add to this collection in the future. So hopefully you'll stick around for the future videos on those processes. But until then, I'll see you later.